So welcome back everyone to the 9th day for ST4. So we are going to have Shouvik's fourth lecture, I think, fourth lecture of Shouvik. So without any further interruptions, let's hand it over to Shouvik, please.
Okay, so thanks and good morning, everyone. So today we are going to see some examples of some systems obeying ETH. So we discussed ETH yesterday. We're going to see some examples. And as I mentioned, I mean, this is not a theorem or a lemma, and one can find examples of systems violating ETH, which are also interesting. And we'll see some of these. Then we'll discuss which are the operators for which the ETH ansatz for matrix elements is obeyed. Then we'll see how to generalize these ideas for integrable systems which have additional conserved currents. And then we'll slowly move to 2D CFTs, and that's the final topic of this series of lectures. We'll discuss thermalization in 2D CFTs and how these ideas to what extent these ideas from ETH hold true in 2D CFTs. And yeah, so we'll also see the notion of typicality in the states of a 2D CFT. All right. Yeah, so let's begin. So just a summary from yesterday, we discussed this ETH ansatz, which is an ansatz for matrix elements of an operator O. And it has got a leading piece. This is a diagonal matrix and times essentially the microcanonical expectation value of this operator O. And you have, this is the subleading term, which consists of the fluctuations. It is exponentially suppressed by the entropy, and it contains a smooth function, Fe bar of omega. So it's the sum of the average energies of this state, and the energy difference between the states. And there is a random matrix part to it. Okay, so this RMN is random variables with zero mean and some variance of order 1. All right, so so in words, what this ansatz for matrix elements says is that you've got smooth diagonal elements, which is this, and suppressed off-diagonal elements. And we saw that the diagonal matrix elements encode the equilibrium values, and the off-diagonal matrix elements, they encode the fluctuations, which should be small at late times. And this ansatz, we almost sort of derived it from random matrix theory. We started with a GOE matrix as our Hamiltonian. We found the eigenvectors, and then we found what are the matrix elements of this operator O in the basis of energy eigenstates. Okay, and from there we arrived at this result for the matrix elements of an operator. And this is closely related to this because this 1 over square root D is related to, yeah, to this, so the rank of the matrix. Okay, so let's begin. So let's look at some examples of some systems obeying ETH. So ETH has actually been tested in a variety of systems, condensed matter systems on the lattice, like spin systems or bosonic systems. So one example is hardcore bosons in 1 dimension. So let's consider this Hamiltonian. So there are L sites, and there is this hopping term. So it can hop. The boson can hop from one site to the next site, in the Hermitian conjugate, and then this is a potential which is constructed out of the number operator. Right? This is this. Okay. If you just consider the first line, it is actually an integrable Hamiltonian. Okay, and then you can look at the matrix elements of a 2-point function. So this is the number operator at site 1 and the number operator at site 2. Okay, and then you look at the diagonal matrix elements. And then you'll see this scatter plot. This blue scatter plot is for the diagonal matrix elements of this integrable Hamiltonian, which is just the first line. Okay. And you see it's a scatter plot, so it's not smooth. And now if you turn on these terms, if you give a finite value to this J prime and V prime, what happens is that this blue scatter plot, it collapses quite strikingly to this smooth curve. So one of the things about ETH is that you have smooth diagonal matrix elements. All right. And it is very interesting that as soon as you turn on, give some finite values to these coupling constants, then you have got the smooth curve. Okay, so this is a verification of ETH for the diagonal elements. All right, is this example clear? Okay, very good. So now, question. So this is a plot. So this is the matrix plot. Okay, so this is the diagonal matrix elements, and these are the off-diagonal matrix elements. Okay, of some system. Okay, and one of them is integrable, and one of them is chaotic. Now, what you have to do is to just look at these matrices. If you like, you would want to increase the brightness of your screen in order to see what the off-diagonal elements are. So the darker it is, the smaller it is, and the more yellowish it is, the greater it is. Okay. So if you think, so one option is the left one is chaotic, and the right one is integrable. So this is chaotic, and this is integrable. The other option is this is integrable, and this one is chaotic. Now, if you think option B is correct, please raise your hand. Let's take a poll over here. Okay, so it's still increasing, 5 out of 24. I think, okay, so we reached a maximum of 5. So that's like the minority.
Can I ask a quick question?
Can we finish this and then we do that? Yeah. Or do you have any question about these plots? Then I can try to explain a bit more. Or do you have a question about the question or something else?
Not about the plots, but this maybe I have missed this one. This hardcore bosons. Why this is called hardcore?
Yeah. So I'll discuss that. Yeah.
Okay.
Yeah. Yeah. So just think of this as some Hamiltonian, but one should be able to recognize which is chaotic and which is Hamiltonian, which is integrable. Okay. So I can give away the answer. So the people who raise their hands, I mean, B is actually the correct answer. So maybe can one of you explain why do you think it is correct? Why the left one is integrable and the right one is chaotic? Would anyone like to say?
Because the left one doesn't have much difference between the off-diagonal and diagonal terms, and the right one, the diagonal terms are much brighter.
Right. So you think that
this is also relevant here, right?
Yes, that is correct. So the main thing is actually smoothness. So you see over here that the diagonal matrix elements, they are smooth. Whereas in this integrable case, this is not something which is smooth. And one more thing is that this was actually mentioned, is that if you see very closely, some of the off-diagonal elements are of the same order as the diagonal elements in the integrable case, and some of the off-diagonal elements are exactly 0. Okay, so this is a characteristic of integrable systems. Whereas if you look on the plot on the right, you see almost all of the off-diagonal elements are small, but they are non-zero. Okay, and yeah, so this is the way you can visually recognize that the system, that this is chaotic and this is the one which is integrable. Okay, yeah, so now there was a question by Pratik that why are we saying that this is a hardcore boson? So the thing is, in the classical case, so the hardcore boson is like if you have got two balls and they can come close to each other if the radius is r, so the closest distance from the centers can be 2r. And if the distance between these two centers is less than 2r, then the potential is infinite. Okay, so this means a hardcore boson, which can just touch each other, yeah, and bounce back. So the quantum mechanical analog of that is this Hamiltonian. So this is called hardcore bosons in one dimension. So you can also think of it as a one-dimensional Bose gas. Okay, so that's another name for this hardcore bosons. Okay. Any questions? Yes, Pratik.
Yeah, so if we take any boson system and we take the potential to infinite, then it becomes a hardcore boson in some sense.
Yes, that is in the classical case. Yeah, yeah, that is in the classical case. Yeah. So it's just to be precise. I mean, yeah, V of A. Let's call this A. Radius is A. Okay, so it can just be A. Yeah. So V of A is is 0 if the distance between the centers is greater than 2a, and it's infinite for r less than or equal to 2. Yeah, so that's the classical version of the hardcore boson, and yeah, so this is the quantum mechanical analog of that. So you have a Bose gas, I mean, which can.
Yes, so if we take the Hamiltonian and just say that it is just an integrable system, so J prime and V prime is 0.
Yes,
so
yes.
So if we also take V, the potential V in the first line also is infinite, then it also becomes a solvable system. I mean, it's integrable.
Yeah. For any value of J and V, it is a solvable system. Yes.
Okay.
So, by the way, this is just a number. This is not related to this. So this is in the classical case I described. Okay. I hope this is clear to you. So this is just a parameter. In the quantum case, this V is just a number. But the classical analog of that has got this.
But V turns out to be this on-site potential, right? With just an
yes.
N and J plus 1.
Yes. So Nj is Bj dagger Bj. Okay. And this is another Bj plus 1 dagger Bj plus 1. So this is like a quartic term, quartic boson term. Okay, so that's the coefficient of the. This is a quartic coupling. Yeah.
Okay, thank you.
Yes, Akhil. Only a difficult question.
The second line alone should also be integrable, right?
I'm sorry, I cannot hear you properly.
The second line of the Hamilton alone, if the first line
Akhil, sorry, we can't hear you.
Should be integrable.
Okay, yeah, but I could make out. Yeah, and so Akhil is asking if we just take the second line of the Hamiltonian, it should also be integrable. Probably yes. I don't know. Yeah.
I mean, it's already just. Am I audible now? Sorry.
Yeah.
So it's just hopping by 2 terms.
Yeah. This is instead of hopping by 1, it's hopping by 2. Yes, probably it is. Yes. Yeah.
And I would have thought, like, if you think about the system in some RG kind of way, like both the second line adds qualitatively doesn't add anything, right? It just adds another hopping by 2 points. It kind of is like making a nearest neighbor interaction kind of system to some
Yeah,
nearest term
next to nearest neighbor interactions. Yes, and that is chaotic. Yeah, if you have both, that is chaotic.
and suddenly that makes it all chaotic.
Well, I mean, if you smoothly tune these values from 0 to thing, like, I mean, you have to put some amount of finite values, and then, yeah, you will see that this thing collapses to this.
So, maybe I'm very naive, but like, do you know what this system flows to? Like, say,
No,
if
no,
you
no,
have-
I don't know. I don't know. This is not my domain of expertise. Yeah. So, yeah, I don't know.
But it's very surprising, right? Like, if you have a hopping in two nearest neighbors, it's not chaotic integrable, but like, and naively, like, if you just add one more lattice of hopping, it suddenly becomes chaotic.
I don't have anything more valuable to add. Any other questions?
So the point smooth diagonal elements in the non-integrable case
Mm-hmm.
is you can see like you can prove or you have seen for many systems. That's why you have written that.
Yes, you have evidence coming from many systems. Yes. Yeah, and you know, the ETH ansatz, as we saw, it also you need, so the smooth diagonal elements, as we saw yesterday, it is needed in order to erase the memory of the initial state, right? So it makes you know, that was a requirement for thermalization, and it's satisfying to see that happens also over here in an explicit example.
Okay, no, I'm not understanding. Smooth means it should be integrable, right? Like it has thermal.
No. So recall what we discussed in the previous lecture. So we saw that there was this long time average, which we looked at, and the long time average went as Cm squared MOM, okay? And this had memory of the initial conditions because of the appearance of this, because your initial state at t is equal to 0 is given by Cm M. Okay, so this has the memory of the initial state. Now we said that if this is smooth, you can factor this out of the sum. Okay, this is a sum over closely spaced eigen functions. I mean, with closely spaced eigenvalues. So this is mod Cm squared, and this thing is just this. Okay, so the smoothness entered over here. So it's a property of chaotic systems that diagonal matrix elements should be smooth. Yes. Okay, so I think I can go on.
Just a clarification. So is that smoothness and suppressed off diagonal and if and only if statement kind of like?
You mean if and only if it's smooth
As in
and
yeah, if it's smooth and off diagonals are suppressed, am I kind of guaranteed some kind of chaos? Like I kind of
yeah.
see that you are motivating that
Yeah.
ETH
Yeah.
wants that, but
Yes,
is the
yes,
other way also
yes.
Thanks.
That is correct. Yeah. Okay, so this is yet another example, but a different kind of interaction term, which you can add. This is another integrability breaking term. So what you see is now the off diagonal elements now. So in the so what you see over here is that in the integrable case, so this red line is the moving average. Okay, so this is the integrable case and this is the non-integrable case. So you see in the integrable case, so this is one observable and this is another observable. So the blue dots is one observable and the green dots are another observable. So you see in the integrable case that there is a huge spread from the average value. Okay, whereas in the chaotic case, comparatively the spread is smaller. Note that we discussed yesterday for the off-diagonal elements, the mean is 0 and the variance is suppressed, is e to the power minus s by 2. Okay, And we see that the variance is actually small for the non-integrable or the chaotic case, whereas it is quite large for the integrable case. And moreover, a large fraction, it may not be visible here, but what actually happens is that a large fraction of the off-diagonal elements are exactly zero in the integrable case, as opposed to the non-integrable case, where you have the off-diagonal elements to be small, but most of them are non-zero. So because of selection rules in the integrable case, it forces some of the off-diagonal elements to be exactly zero, and some of the off-diagonal elements to be large. As we saw in this previous example, if you see very closely, some of the off-diagonal elements are quite large, and some of them are exactly zero. So having such a structure of the off-diagonal elements, some of them large and some of them exactly zero, does not allow for phase cancellations, okay? So the phase cancellations is required in order to have thermalization. So which actually happens in the chaotic case, but in the integrable case, it is absent. Okay, so this is just what I just mentioned, that a large fraction of the off-diagonal elements turn out to be exactly zero in integrable systems. And this is because of the selection rules. And some of the off-diagonal elements are actually turn out to be quite large. Yeah, and this does not allow thermalization as we do not have phase cancellations. Yeah, and we see in chaotic systems or systems which obey ETH that off-diagonals
Shouvik seems to have internet problems. Hello.
I can hear you.
Yeah. Shouvik. He says that he will be back.
Okay, so yeah, so any questions? So we saw some examples, and do you have any questions? Yes, Akhil again.
Hi, were the lattice actions all 2D or does it?
It was all 1D. Yeah, but there are some 2D examples. I mean, one can look at the Ising model, and with the 2D Ising model with magnetic fields turned on in both the directions, both the two spatial directions, and that is again chaotic. If you have the magnetic field turned on in only in one direction, then it is integrable. But yeah, if it's turned on in both directions, then it's chaotic. Yes, so this is all 1D. Yeah.
Sorry, could you say that again? Like magnetic field turned on in two direction is like magnetic field turned on in the diagonal, right? Sorry, maybe I missed it.
Diagonal? No. I mean, consider that 2D Ising model on a plane. and you have two spatial directions, and you turn on magnetic fields corresponding to both these directions. Yeah, that is an example of a chaotic. That is going to have chaotic features. Yeah, so in the review, which I have put in the as references on Slack, maybe you can check it out. I mean, there are some more examples which are considered over there.
So would you say this chaos is not a like a thing you can look for from the IR or something that you have to look at the UV Lagrangian? Is that a right way to think? Because in 9D thinking, all these things would float to some like even if you have icing at 2-direction magnetic field, like if you had if in the continuous limit of the lattice, it's just turning on magnetic field in some one diagonal direction, right?
Yeah. Yeah, I don't know. I don't know what is the answer to this question.
Okay, maybe in a CFT, like does it matter whether you have the CFT and you turn on an irrelevant coupling and the chaotic property really differs? Okay.
Yeah, even within CFTs, we don't know an example which obeys the ETH ansatz completely. Yeah. So, and you know, if you turn on couplings, it's a very difficult question. Usually, you have to do conformal perturbation theory, and then it's a mess. I mean, it's hard to, do. I don't think we have calculations to answer your questions at the moment. I mean, we don't have anything explicit so far. Yeah. I must see there is a question.
Yeah, so does it mean if a system is not integrable, it is chaotic?
Oh, well. Well, I mean, thing is, you consider a particular system, and then for some regime of parameters, it is integrable, and then beyond that regime, I mean, if you tune your parameters correctly, you can arrive at some chaotic regime. How universal? I mean, this is something which is done on a case-by-case basis. I mean, it's not easy to make universal statements. I mean, there can be okay. So one example which I can say is that we saw that the level spacing distribution obeys Poissonian statistics in the integrable case and Wigner-Dyson statistics in the chaotic case. Okay. Now you can turn on smoothly change some parameter, and then you will see the transition from the Poissonian to the Wigner-Dyson. But there will be stages in some, I mean, there will be some regimes of parameters where it is neither Poissonian nor Wigner-Dyson. Okay, and it's not something like a sharp change. It's a smooth crossover.
In between also there can be some phase.
Yeah, in between also there can be some things. Yeah.
Oh.
Yeah, but ETH describes the chaotic regime. That's what the thing is. Yeah. Okay, so can go on. So let's look at some ETH violating examples. So once again, just want to reiterate that ETH isn't a theorem or a lemma or an axiom. It should be thought of as a criterion for systems to thermalize. And one can find examples of systems that violate ETH, or one can also find states in a system which violate ETH and states in a system which obey ETH. Okay, so that's the next statement, which is in a given system, there could be states that obey ETH and states that do not. We'll see what some examples. Okay, so the first example is this class of systems that fall under this category of many body localization. So these systems have got strong disorder, which can localize electrons and prevent transport from happening. So in a perfectly clean crystal, your electron wave functions, these are block waves, okay? And they can, the potential is such that they can hop from one side to the other, and thereby you can have electronic transport, which can transport heat, for example, or electrical conductivity, for example. But there can be a disorder in the system, okay? So this disorder deforms this potential of that of a clean crystal, and at some lattice sites, the potential the potential well is deep enough. It can actually trap the electron wave functions. Okay, and these electrons over here will find it difficult to hop from this site to the next site. Okay. And thereby, these systems can retain memory of the initial state. And you can look at the energy eigenstates of the system, and these energy eigenstates, they do not obey ETH. Okay. So now, this is a real experiment. So it's also a trending topic in experiment, and a lot of the work that happens in this field is motivated by some really great experiments. So one can actually look at bosons. You can look at, so actually this is, I think it's 2D bosons. So it's, you can look at bosons on a plane, and then you can engineer some disorder in the system. So this is again realized by this Hamiltonian over here. So U over here is some, again, some quartic coupling. And this delta is some disorder which is picked from this distribution. Okay, so this delta over here. And you can do an experiment. If you have this delta to be 0, okay, so this is if you do not have disorder in the system. So you can make a configuration in which all so you do this experiment with rubidium atoms. You can make a configuration in which these rubidium atoms lie in a half circle on the left, okay? And the disorder is 0. So as you let it time evolve, it spreads out and it becomes a circular thing. Okay, so this is just a visually enhanced image. So it's on the left at t is equal to 0, and as you time evolve, it spreads out and becomes circular. Now let's look at the case with non-zero disorder. So if you have non-zero disorder, so this part is actually non-zero, and you turn on this disorder and you let it time evolve again. So you have the same configuration as over here, and you let it time evolve, and you can clearly see that the atoms actually continue to live on the left side. Okay, so it clearly preserves the memory of the initial state. You can say that the initial configuration actually stays in shape at later times. So so this is very explicit, and you can do an experiment and see this for real, that that actually happens. And this is also useful from a technological standpoint, because the systems with many body localization, they can serve as quantum memories, in the sense that they can preserve the memory of the initial state if you engineer it in a proper way. Yeah, so this is an experiment conducted not too long ago by these people. Okay, so so the next thing. So any questions about MBL? I didn't have too many slides. I mean, I'm not discussing it in detail. But any questions? Okay, so so the next topic is quantum scars. So these are some special states in your system which do not show thermal behavior. So one can look at a chaotic system, and an overwhelming majority of states are going to obey ETH. It's going to thermalize, but there can be some special states which do not obey ETH. Okay, so one example is let's look at it classically first. So we have this billiards again. So in this stadium, so we know that if we start with if a ball starts from here, then it bounces back and forth between the walls, and then it essentially fills up this stadium. Okay, so that's the chaotic behavior. But you can like adjust the angle, the launching angle of your ball in such a way so that it bounces back and forth between these horizontal lines, and it undergoes almost like a periodic motion between these two walls. Okay, so this is a very special state. Okay, and it does not quite fill up the entire region. Okay, and the quantum analog of this is that for a generic state, which is classically chaotic, the quantum analog of that is a random superposition of plane waves. Okay, so that's this thing which you have over here. It's very chaotic and random. On the other hand, the quantum analog of this state, which bounces back and forth between these horizontal walls, is something like this. So you have something like a standing wave, roughly speaking, between these two walls. Okay, and this looks like a stable configuration. Okay, so this is a state. It's not going to. It's going to like if you make a superposition of initial states of states of this kind. I mean, it is not going to thermalize. It is yeah. So this is a special state. So, yeah. And similarly, you can look at some lattice systems. The details are not important. So usually, if it's chaotic, then you can look at the entanglement entropy as a function of the energy. So this is entanglement entropy of excited states for some given subregion, for a fixed subregion. And all of them obey, so like they have a volume law like entropy, entanglement entropy, since it's an excited state. But you can add some potential and design it in such a way that there will be some special states whose entanglement entropy is going to be much lesser than most of the excited states. So these are these red dots over here. Okay, so so these special states are called quantum scars. So these are special. Okay, and actually, in the billiard example, one can actually find some states which are more or less yeah, whose classical trajectories are stable, and their quantum analogs are the quantum scars. For instance, in this example over here, so you see that the wave function is sort of peaked in these darker regions. And the classical analog of this is that, of this one, is that if you launch your billiard like this, so it bounces off this wall, and then it goes here, and then it goes here, and then it bounces back over here, and then it goes here, and then it goes here, and here, and here, and so on. Okay, so it's can you actually see my writing or no? Yeah, you can't see the pointer. Just a minute. I'll just, so I'll join from my iPad again, and can you please make me the co-host? I guess you can see now. Can it be seen, my writing?
Yes, yes.
Okay, thanks. Yeah, so if you so in this configuration, so in the quantum case, it's the wave function is the norm of the wave function is actually peaked in these darker regions, and the classical analog of that is that if you launch your billiard from here like this, so it gets reflected from this wall, and it comes over here, and then it comes over here, and then it comes over here, and then it goes here, 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 and so on. It's almost like a periodic orbit. Okay, so that's a very special trajectory. And similarly, or in this case, in the second one, you can launch your billiard from here, and then it bounces back from this wall and comes over here, and then it again bounces, reflects back from this wall, again reflects, and again this continues. And this is a superposition of the other one, which you can launch from here. You can launch from here, and it bounces from this wall, and it bounces back. And this is what happens. Okay, so that's the classical trajectory. And finally, in the last one, you can launch it, launch your billiard from here. It bounces again here, 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 and so on. So it kind of follows again this almost periodic trajectory. So these are very special ones, special classical trajectories whose quantum analogs are have got some symmetries and so on. But these are very special atypical states, and these states will not obey ETH. Yes.
Why in the first one it is not following that trajectory? Others seem to be following.
Yeah, it's almost doing that. It's, or maybe I did it wrong, but it's almost doing that. Yeah, you can associate some classical trajectory to that. Yeah. Or maybe I don't know. Maybe you can launch it from here, and then it just goes back. Something like that. But you can clearly see that there are some symmetries, right, in the wave function. At least some Z2 symmetry is present. Yeah.
There is a question in the chat by Akhil that whether these quantum scars are similar to the localized states.
Well, I think in MBL, all the states of the system do not obey ETH. But in an example such as this, I mean, there are only some special states which do not obey ETH. Yeah, so it's a bit different. Yeah. So when you refer to quantum stars, you are referring to a special class of states in a chaotic system usually. But MBL, most of the states, I mean, or all of the states, do not obey ETH.
So when MBL happens, most states localize. Is that the statement?
Yeah. That's right. Yeah. That's because of the nature of the potential. Yeah. Yes, Pratik.
Yeah. So so along with this line of previous question, so is it this quantum scars are basically close to the ground state following area laws or something?
Yeah, it's somewhere in between. Yeah, it's hard to pinpoint. Okay, first I should clear this. Yeah, Pratik, could you please lower your hand because my yeah. Okay, thanks. Yeah, so it's hard to say. Like some of them might follow the area law, but not all of them, because you see from here, like the entanglement entropy, like kind of lies. Yeah, in between, like, you know,
so typically the excited states in generally follows this volume law. So but the ground state and the low-lying excited state, low-lying state, that's so I'm just wondering where these kind of states lying. I mean, between these, what is a special case?
Yeah, so it depends on the system. I mean, in this case, I have not written the Hamiltonian. But yeah, it's not necessarily all of them follow the area law. Well, this plot is for a fixed subsystem size, I should mention. But
oh, okay.
So, and you're changing the energy. Yeah.
Oh,
Yeah.
so you're not changing the fraction of substance.
Yeah, I'm not changing the fraction, but
Okay.
you can look at some examples probably. This is actually
But
there's a very nice recent review by these three authors who can look at that. Yeah.
But it's very similar to if you change also the fraction, right? If it follows the same law, same kind of.
Yeah, if it's a 1D system, then it should be something like this. I mean, like a straight line.
Right.
And yeah, we'll see it in a few slides. Yeah, but yeah, this on the right hand side, this is the plot against the energy. Yeah.
Okay. Thanks.
Because you ask, actually, yeah. So you see, E0 is the energy of the ground state. Okay. So when it is 1, so yeah, so when it is 1, so I think the ground state is somewhere here. I think if you see closely, there is a violet spot over here. But I think the entanglement entropy of this scarce state is even lower than the ground state entanglement. Yeah. And for the others, it lies somewhere in between. Yeah. At least for this system, this is what happens. You can probably find some other examples where all these scars they have similar to area law entanglement. Okay. Yes. Yes.
Yes. So in the previous image that you were showing.
Yes.
So over here, what do you exactly? So how do we specify a system per se? Do we specify it by the Hamiltonian that we're looking at? Or,
yeah.
Okay.
Yeah.
And over there, so in these two cases, why are these things different? There is a different potential present, which you have written H plus V.
Yes,
Okay.
yes. So if you have this H, then yeah, it does not have any scars essentially, or very few of them, if you like. Okay, just these three. Okay. But this V is engineered in such a way so that you can have much more. Yeah.
Okay, so what you are saying, if we control the launch angle in some way,
yes,
probably in the left hand picture, that corresponds to changing this potential V.
Yeah. So no. So that's a different kind of thing. So so over here you're creating scars by changing the potential. Okay, but in the stadium problem, you're not doing anything new. Even with this potential itself, you can find some scars. Okay, is that clear? Because I'm saying that with this is already an analog of this. That's what I'm trying to say. Okay. Yeah. So
okay.
Even with this stadium potential, you can find some scars. Yes, Orgo.
So can I just go to next slide? So all these states, so I'm just, I mean, probably a very stupid question to ask, but anyway, all the states, do they need to have these scars need to include the boundaries as their points, even in this picture? I mean, the way you are describing, there was like the park contours are like classic, not contours, like they are like classical paths. So particles are like bouncing from the boundary. But is there anything that is all closed inside?
Yeah, it's all closed inside. I mean, so the analogous quantum mechanical problem which you solve is V is infinity outside the stadium and V is 0 inside the stadium. That's all. Yeah. So
no, I'm saying there's something. Is there any can there be any closed scars inside without including the boundary points? I mean, only inside.
Okay. Oh yeah. Okay. Yeah, I don't know. Yeah, maybe there can be. Yeah.
I mean, in principle, there's no objection to that.
One point I would like to make is that at least in these cases, I'm making some identification with classical trajectories. Okay, this is kind of heuristic. I mean, there might be some scars which have got no classical analog.
Right. That's what I was. No.
Yeah. And then such things might exist. And then.
Okay. Thanks.
Okay. Any other question? All right. Okay, so finally, I come to this notion of typicality. So this is just empiricism. So I'd like to say that in a typical year, there isn't a global pandemic. So 2020 and 2021 are not typical years, okay? They are special years. So just carrying this idea to thermalization of systems. So you say that, okay, for typical states, so which is like an overwhelming vast majority of states, so the high energy pure eigenstates, almost all of them, they mimic thermal behavior. Okay, so this is a weaker statement than ETH. So the strongest form of ETH says that this is going to be true for all states in your system. Okay, so this is too strong, but you can slightly weaken it and then say that okay, so this is true for almost all states, for typical states. Okay, and we'll see what typicality precisely means in 2D CFT. I mean, you can make this idea precise. It's not just words. Okay, so you can make this mathematically precise. Okay, so this is a weaker form of ETH, and ETH applies to all states in the system. Okay, so I think I come to an end of this part. Yes, Siddharth?
Yeah, sorry, Shouvik. I wanted to ask you, I wanted to ask about these quantum scar states. I didn't quite get. I got that they're special states that don't thermalize, but how are they different from? I mean, you know, there are several examples of states that don't thermalize, right? What is their defining feature? Like you were saying that in the class, if you take the classical limit, there are some periodic orbits, and so on. But
yeah. So the defining feature comes about by looking at some quantities. So over here, for example, you look at some look at the entanglement entropy for highly excited states. I mean, they obey the volume law. Okay, and they will obey the volume law. You don't see the volume law over here, but they obey the volume law. But clearly, these have much lesser entanglement compared to the other, most of the states. Okay, so that's one defining feature. Another defining feature is that this relation, okay, if you choose some observable, this relation is not going to be obeyed by the quantum scars. So the entanglement entropy comes from the reduced density matrix. So you can look at the reduced density matrix of a quantum scar state and calculate the entanglement entropy, and then you'll see it's much different from the other states which have an energy eigenvalue same as that of the scar state. Yeah, so that's one way to.
I see. And how is that different from these many body localized states?
Yeah, so this was a question which was asked by Akhil. So it's you don't.
Sorry, my internet dropped too. Sorry. Yeah.
You don't think of many body localized states, but you usually think of a many body localized system or a many body localized phase. Okay. So in that phase or in that system, almost all your states are going to violate ETH.
I see.
Whereas quantum scars are special states in the thermalizing phase, if you like. Okay. And these are special states in this thermalizing phase or in this chaotic phase, which do not obey ETH. And there are like very few of them.
And do they appear like through the spectrum? Do you have them like appear all the in some cluster, or do you have them like spaced all throughout the spectrum?
Yeah, you usually I don't know it very generally, but it's usually spread out. I mean, throughout the spectrum, and it's like we are looking at high energies like finite density eigenstates.
And the spacings between these don't follow some.
Yeah, these I don't know.
Some law or anything. Okay.
I don't know this. Yeah.
Okay. Thanks.
Yes, Pratik.
Yeah, maybe you have mentioned earlier, but as you mentioned this typicality, suppose we consider this typical random pure state that Page have considered in his original paper. So this kind of state also follows the volume laws scaling.
Right.
So do they also follow this ETH?
Yes, I think so. Yeah. We'll see. So the thing is, like, you can, we'll see in a few slides, you know, since the volume law scaling for the entanglement entropy. So entanglement entropy comes from the reduced density matrix. Okay. Now, if so, for half the system size, we are going to see that the entanglement entropy of an excited state, it matches that of a thermal state. Okay. So the reduced density matrices, they agree for small enough system sizes. Now, a statement such as this, you can think of it as a consequence of agreement of reduced density matrices. So if the operator has got support in the sub-region of the reduced density matrix, and if the reduced density matrix is essentially the same, then this is just going to follow from equality of reduced density matrices.
Okay, thanks.
Yeah, so there is a nice paper by Garrison and Grover that discusses this in some amount of detail.
Thanks.
Yes, Akhil?
Just a follow up on this question about scarce law. So, like, is there anything more like nicer about scars than they are like some isolated points? Like if I slightly change the shape of the billiard board, will the number of scars be same? That kind of thing. Like, is there something more about the scars and like where they occur and so on? Like, or is it just
you mean some pattern or something? You mean some pattern in the spectrum or something?
Is some pattern in the spectrum of like number of scars or something like that? In the sense, like, are there just some random event that there's a scar state, or if I slightly change the billiard board shape, will the scars go away? Will the number of scars be same? Is that kind of stuff looked at?
Yeah, probably. Yeah. Yes, I don't know. Yeah, you always ask me difficult questions which I cannot answer. Yeah, I don't know whether that has already been studied or not. Yeah. Yes, Banashri?
Hello.
Yes.
Yeah. So if I got it correctly, means a quantum scarcer means you tune your potential to get this scars, right?
What do you tune?
Means there is, you saw a picture, means where there is only the Hamiltonian, where there is not scars, and when you put an extra potential and you got the scars. Yeah. So in classical regime also, can you get by tuning this kind of, can you get scars?
Okay. Yeah, maybe. I don't know. So in this case, I mean, the potential is already designed in such a way that you can get typical states as well as scars. Yeah. So this is, so that, yeah, as I was saying, I think in answer to Pratik's question, you know, the analog of this is this already. The potential is already exists, which is going to allow both scars as well as you know, typical states. Yeah. But yeah, probably one. Yeah, it's a possibility that, you know, you don't have scars and then yeah, you change your potential in such a way so that you can accommodate scars. It's a possibility. Yeah, yeah.
Okay, thank you.
Yes. Okay, so all right, so okay, so we discussed this, and yeah, okay, so now we come to a discussion of which are the operators that will be the ETH answer.
Sorry, Shouvik, just one clarification. Can I say that in you know, if the one difference maybe between the scars and localized many body localized states or integrable, so if you let's say you have I mean, we can ask which states are not ergodic. So if you have integrability, you don't have ergodic behavior.
Yes.
But there you have lots of conserved quantities, right?
Yes.
If you
but that's not the defining kind of like that. That's not the only feature of it's integrability implies absence of ergodicity, but there could be other possibilities as well, which does not.
Right. But I was thinking, what I was thinking is that is happening because you have all of these symmetry structures, and if you slightly perturb them, then you get back ergodicity, right? In the case of integrable systems. In the case of many body localized systems, you also have that's also an example where things are not ergodic, right? But there you have some disorder in the system, right, which is localizing things and preventing ergodicity.
Right.
So here, can I say that quantum scars are those states which don't have either of this? They don't have integrability in the sense they don't have a lot of conserved quantities, nor do they have disorder, but they still have these periodic orbits which are preventing you from getting ergodicity.
Right. So
one difference.
Yes, that's a nice way to put it. But I think maybe you can associate some sort of integrability to these orbits, right? Because these are periodic in some sense. These are periodic, and then and there might be some conserved quantities, some discrete. I don't know. So there are some discrete symmetries associated with these orbits, right? And
right.
So it's hard to associate some conserved quantity because it's not a continuous symmetry. But in some sense, there is some weak form of integrability is there. At least you can predict, very easily what is going to be the orbit at very late times. Yeah. So that feature of predictability is there.
Right. But it doesn't have, at least in the sense of I guess at least if you look at continuous symmetry, it doesn't have these like integrable systems which have like a ton of conserved quantities. That is not there.
Clearly, clearly it's very different from those.
Right.
Okay. But some discrete symmetries are present.
But discrete symmetries are okay.
At least in this example.
Okay, thanks.
Okay, so now we come to a discussion of which are the operators that obey ETH. So I think I have around 20 minutes left. Is that correct? Yeah. So maybe so I wanted to discuss this part about which operators obey ETH, and I wanted to also discuss integrable systems a little bit. And so I'll not talk about 2D CFTs. I don't think I'll have time, but let me try to finish these two parts. So let me try to finish this part, and then we can stop for questions, and then I'll do the remaining part on integrable systems, and then we can have questions. Is that okay?
Anyways, like you have one more lecture, so fine.
Yeah, so but I want to start with 2D CFTs from tomorrow. I think that's a good place to start things.
Okay.
And let me try to finish the general discussion about thermalization by today. Okay, I think that would be something reasonable to aim for. Okay, so which are the operators that obey ETH? So there's this idea that few body operators are the ones that obey the ETH. Okay, so these are local operators, which means their spatial support is much smaller compared to the size of the system. Okay, so in terms of correlation functions, we expect to recover thermal results for sufficiently low point correlation functions of local operators. Okay, so for example, you can consider a 2-point function. So this on the left-hand side, this is the thermal 2-point function. Okay, and on the right-hand side is the excited state 2-point function. And in a system that obeys ETH, that you can see that sufficiently low point correlation functions can show this equality between the thermal state and the excited state. Also, notice that yesterday we said that these operators, while deriving these things from random matrix theory, one of the things we assumed was that the eigenvalues of the operators, the square of the operators, this is much lesser than the number of degrees of freedom, or the size of the Hilbert space. Okay, so this is a light operator in that sense. Okay, so it's the energy. It's the energy associated to each of these operators are small. So you're working in the probe approximation, which probably you might have heard of if you're used to ADS-CFT. So it should not bring about changes to the system we are probing. Okay, so that it should be in the probe approximation. Okay, if you try to translate this statement to a statement in the gravity dual, it means that these probes should not back react on your ADS geometry and change the geometry. Okay, so they should be light enough. Okay, so here it is. Yeah, so so ETH holds for like local, simple, and nice operators. And so as we saw, ETH postulates that the diagonal elements are smoothly varying for eigenstates within a small energy window. Now, you can interpret this that the operators are simple enough, okay, that it cannot distinguish between nearby eigenstates. And that is the reason that leads to this smoothness, okay? If the operator was complicated enough, okay, it would be able to do a very fine distinction between eigenstates of nearby energies. But the operator is simple enough, so it treats eigenstates of close by energies almost same as each other. And that's the reason you've got diagonal matrix elements to be smooth. Okay, so it comes from the inability of the operator to distinguish between nearby states. Okay, and of course one can find operators that violate ETH. It's not very difficult to find them. So a simple example is this projection operator. So you look at the projector into a single energy eigenstate, and you can calculate its energy eigenvalue, its matrix elements. And clearly, this is just a matrix. This would be just a matrix. Most of them will be 0, and all the diagonal elements will also be 0, other than the nth one. Okay, everything else will be 0 for this projection operator. Okay, so this clearly violates ETH. It doesn't obey the ETH ansatz of having large diagonal elements and suppressed off diagonals. Most of them are 0. So since we are working with orthogonal states, I mean, all of these are 0. And one way to think of this is that this projector belongs to a single mode in momentum space. So it's a fixed energy. You can see it's a momenta to it. So it's sharply peaked in momentum space, it's like a delta function. Whereas in position space, if you Fourier transform it, it's got infinite support in position space. So it's not really a local operator in position space, and that's why it violates ETH. Okay? ETH holds for local operators, and yeah, so this is like clearly non-local in position space. And yeah, so we discussed a little bit about entanglement entropy. So as I was saying, ETH can be viewed actually as a consequence of an agreement of reduced density matrices, which is this statement that you look at the reduced density matrix of excited state. You identify the energy of that excited state with the temperature in the usual way, which we talked about. And you compare the reduced density matrix of that of a thermal state. Okay, and there are some quantum information measures by which you can do this comparison. For example, you can look at the relative entropy, you can look at the trace square distance. Okay, so there are some quantum information measures which you can find that can compare two reduced density matrices, and it is 0 if the two reduced density matrices are the same. So we can see this. So yeah, so you can consider a 1D system, look at the entanglement entropy of this finite subregion, and the density matrices will agree if ETH is obeyed. And obviously for scarce states, this is not true. And this is the idea of subsystem ETH, because you're looking at the reduced density matrix of a subsystem. And sorry, I spelled entanglement wrongly over here, but the disagreement of the reduced density matrices, it implies that entanglement entropies in particular should agree, okay, to some approximation. And yeah, you can verify this explicitly in a system. So this is this system over here. So this is the Ising model with magnetic fields turned on in 2 horizontal directions. I think it's called the XXZ if you have this term switched off. Yeah, but I don't know the terminology too well. And you can indeed verify that the entanglement entropy matches with the entanglement entropy of the excited state matches with the entanglement entropy of the thermal state. Okay, so so this was performed. So it's a result of a numerical exercise. So this was performed with 21 lattice sites, and the subsystem size is 4, so it's sufficiently small. And this is a plot of the how the entanglement entropy changes as you tune the energy of the excited state. All right. So so this blue dots over here, they correspond to the entanglement entropy of the excited states, a single excited eigenstate. So this over here, and then this green line over here is the entanglement entropy corresponding to the thermal state. Okay, and it shows very good agreement. Okay, and this agreement is for system sizes less than equal to half of the volume of the system, of the full system size. Okay, and that is because of this, because since if you have a pure state, S of rho A is equal to S of rho A complement, right? I think Jyotinmoy discussed this in his lectures, that if you find the entanglement entropy of this region, it is equal to the entanglement entropy of the rest of the region, if the state is in a pure state, but it's not true for a mixed state. So you can see how the entanglement entropy changes, or the Renyi entropy changes, as a function of the subsystem size. So for half of the subsystem size, so up to half of the subsystem size, it grows. So and it matches. So this dotted line is the entanglement entropy of the thermal state. So it keeps growing forever, like a volume law. But for the entanglement entropy of the excited state, it grows up to half the region. And since you have S of A is equal to S of A complement, it goes back down. I mean, after half of the system. Okay, so you can see the agreement up to half the system size. As we already discussed, for the ground state of the vacuum, the entanglement entropy is like an area law. And for the excited state, it grows as the entanglement entropy goes as the volume law. Okay? And for the Renyi entropies, you can see some agreement for extremely small subsystem sizes, but for higher system sizes, for greater system sizes, it stops agreeing. And you know, this is the thermal line, and this is the excited state line, and it's different. So the Renyi entropies, yeah, so it's a very fine-grained probe, and they don't match, I mean, with the thermal state and the excited state. Yeah, okay, so we can stop here and we can discuss a little bit, and yeah, if there are any questions about this part. Okay, so seems there are no questions, so I can go to the last section for today, which is a discussion on integrable systems and how these ideas from ETH can be generalized to that context. Okay, so one example of an integrable classical system is that of the Newton's cradle. So you have this set of pendulums, and then you let one of them go, and it hits the other ones, transfers the momentum, and then it keeps going forever, just like this animation, and it keeps going forever because there is no friction, right, or dissipation. Okay, but you can realize this in a quantum setting. For example, consider the 1D Bose gas again. And you can make a harmonic potential. Okay. And then you take two Gaussian wave functions and with opposite momenta. Okay, so this is a superposition of two Gaussian wave functions, one with momenta minus k and the other with momentum plus k. Okay, so this is a superposition of them. All right, so this is, you'd start with, this is time t is equal to 0, okay? And then you let the system evolve. Okay, so this is just a harmonic potential, which you can solve exactly. And you start with this initial condition and you let the system evolve. And what you see is that since these have opposite momenta, these Gaussian packets, they go apart, you know, and they have some energy and they go apart as far as they can, then the potential forces them to go back. Again, they hit each other, again, they collide, and they go back, go far apart and go back and go away and so on, okay? So this is like a periodic motion and it's integrable, okay? And once again, one can do and experiment. This was very concretely realized in an experiment using rubidium atoms again. You can engineer this potential using optical means. So you start at t is equal to 0. So these are your wave packets which you have created using this rubidium atoms. And these have got opposite momenta, and you let it time evolve. So you start from here, okay? Then these two come close to each other, they meet each other. They become one, and they separate again, and then they go far apart, again collide, and go far apart, collide again, and so on. Okay, and this thing continues over and over again. So this is an example of an integrable system which you can engineer in a lab, and very explicitly you can see that the memory of the initial conditions is clearly preserved. Okay, so this goes on forever. Okay, so it's kind of a famous experiment. I mean, if you talk to people from the integrability community, I mean, some of them refer to this experiment as the victory of integrability. I already mentioned about this slide, so let me go to the next one. So how do we interpret this? So this is, we just saw an example of a state in an integrable system which clearly retains memory of the initial conditions and it does not thermalize. So integrable systems, have a lot of conserved quantities, so it equals the number of degrees of freedom. In the quantum case, if you have an infinite dimensional Hilbert space like a field theory, then you have an infinite number of conserved quantities, and it's an integrable system. So usually you don't have smoothly varying diagonal elements. If you look at matrix elements of some observable, you usually don't have smoothly varying diagonal elements. However, what you can do is to restrict to a small window of energies and also a small window of these additional conserved charges. Okay, so you can slightly generalize the ETH ansatz. So this was actually one of the questions which Pratik was asking on Slack. So you can slightly generalize the ETH ansatz. So now your states of the theory, of the integrable theory, are going to be labeled not just by the energy, but also by the quantum numbers associated to the conserved charges. Okay, now you can focus on a small window of energies as well as a small window of conserved charges as well. Okay. And within that small window, you can writes down an analogous ETH ansatz, that the diagonal elements at least, they are smooth within this small window of energies as well as conserved charges. Okay, so which means that you have to fix the energies and charges about some mean value. All right. And so the thermodynamic description, so this was a single state description. Okay. So the mixed state or the analogous thermodynamic description of that is given in terms of this generalized Gibbs ensemble. Okay, so in this generalized Gibbs ensemble, you turn on chemical potentials corresponding to all the conserved charges. So your Boltzmann factor becomes generalized from e to the minus beta h to with this part, okay? So in which you have turned on chemical potentials conjugate to all of these conserved charges. Okay, so that's the generalized Gibbs ensemble. And what does this mean? We can say that the system sort of relaxes or thermalizes to the generalized Gibbs ensemble, but relaxes or thermalizes should be in quotes, because note what happens. So you fix these chemical potentials. So how do we fix the chemical potentials? So we compare the energy, which is now a function of the inverse temperature, and all the chemical potentials. So this is the grand canonical free energy, if you like. And this is the energy of the excited state. Okay, so you compare these two quantities. Analogously, you look at the conserved charges. You look at the conserved charge, which is in this ensemble. Okay, in the conserved charge in this grand canonical ensemble is now a function of beta and all the chemical potentials. Okay, so you can, this quantity is just the I should write this. So this qi is nothing but the d mu I derivative of the partition function. Maybe there's a minus sign. Okay, so it's a function of the inverse temperature and all the chemical potentials. Okay, so this is the conserved charge in the thermodynamic description, and this is the conserved charge in the single excited state. Okay, and you can work with the initial state and find what these conserved charges are, or what the energy is, because these are conserved quantities. They commute amongst each other, and they also commute with the Hamiltonian, and they remain preserved under time evolution. Okay, so you have a set of n equations, or n plus 1 equations. Okay, so you have n conserved charges, chemical potentials corresponding to these, and you have the temperature. So you have a total of n plus 1 equations, and your unknowns are basically this beta and this mu i's. Okay, this n plus 1 unknowns. So you can solve these equations, this one and this one, in order to find what these are. Okay, and all of these chemical potentials and this inverse temperature, they are fixed by the initial state. Okay, is that clear? Because this right-hand side comes from the initial state, and this gives you a set of n plus 1 equations, which allows you to fix the inverse temperature and all the chemical potentials. Okay, so there are n plus 1 equations with this n plus 1 unknowns. So all of them get fixed by the initial state. So this is a fully constrained ensemble in which you have the temperature as well as all the chemical potentials to be fixed by the initial state. So you can say that the system relaxes or thermalizes to this generalized Gibbs ensemble, if you like, but in a sense, the memory of the initial state is not actually lost, as we saw in the experiment, that wave packets actually came, collided, and went back, and it had a periodic motion. So the statement is that the memory of the initial state is not lost, but it gets stored. The memory is actually stored via these chemical potentials, via these equations, actually, this one and this one. It's because like this depends on the initial state. You can fix these chemical potentials using the initial state. And so it's a fully constrained ensemble, and the memory of the initial states gets stored via these chemical potentials. Okay, so that's the description for integrable systems. Okay, so yes, I'm going to stop here for today. Yeah, so thanks for your attention, and yeah, we can pause for questions, comments. Yes,
Yes, so I was wondering, so is it right to say that the overall statement of ETH would be, for example, the way you described the subsystem ETH, overall statement, could we make out something like that thermal state looks very similar to typical pure states? That's
right.
what the overall statement should be. And in terms of entanglement entropy, I was wondering, since the thermal state is believed to be a mixed state, now when I'm computing entanglement entropy of mixed state by computing, let's say, relative reduced density matrices and so on, does it really show me entanglement? Because there is this belief that entanglement entropy doesn't really quantify quantum entanglement between parts of mixed states. So when we say, yeah, so when we say we are measuring this entanglement entropy for this thermal state, what is this measuring, or what does this mean in terms of ETH?
Yes, yeah, that's a very good question. Yes, indeed, it is correct that entanglement is not a good measure for mixed states, but you can do other things. You can compare these two reduced density matrices, for example, using, let's see, you can use the trace square distance, for example. So let me call this rho. Let me call this sigma. Okay. You can calculate a quantity like this, trace of rho minus sigma squared. Okay, and then you can try to find what this is. So in 2D CFTs, we actually did this calculation. If you look at small subsystem sizes, you can look at this quantity in a small subsystem size expansion. Okay, and then you can verify actually at large central charge. If you take this excited state to be a primary state, and this, if this is a thermal state, then you can actually verify that this goes to zero, at least perturbatively in a short distance expansion. Yeah. So this can be one measure. You can also work with, instead of, you can look at the n, trace square, like n trace distance and so on. I don't know whether you like relative entropy or not, but that can also be another way to look at it.
Yeah.
Anything,
so,
any of these distance measures that involve two reduced density matrices, I think can serve as a good comparison, good measure for comparing these two reduced density matrices.
yes. And as we are talking about this small subsystem limit, does it have to do with, for example, if I choose one subsystem to be small, then the complement is automatically most of the system, almost covering the whole of the system, which is again sometimes believed to be, if we take one of the subsystems to be almost the full system, then entanglement entropy for the thermal state is supposed to give me a thermal entropy. Okay.
Right. For the mixed state, for the thermal state, yes, that is correct. Yes, I mean, if this is equal to the full system size, then the entanglement entropy is the thermal entropy for the mixed state, for the thermal state. But you see over here that if you, for the pure state, if you take your system size to be the full system size again, which is somewhere over here, then it again goes close to zero for the pure state. Yeah. So beyond half the system size, I mean, it does not agree. The density matrices does not agree. Yeah. So you can only make a comparison in this regime, in this regime, for half system sizes. I think he left.
The internet connection is a bit faulty.
Yeah.
So.
Yes, but just to,
He's here.
You're back. Yeah, so I was saying that, this comparison is good only for half system sizes. and yeah, so and one can see an agreement. One can probably try to compute this non-perturbatively as well. I think probably in CFT this might be hard to do, but not in a short distance expansion, but non-perturbatively for finite system sizes, and then also see an agreement. But for lattice systems, one can do this. I mean, yeah, verify that such a thing happens. I mean, the previous slide. In the previous slide, yeah. So this is some finite. You can, instead of the subsystem size to be 4, you can take it to be something like 7 or something, and then again you can see an agreement between the thermal state. Again, this is entanglement entropy, but you can find the trace square distance and then see that it is also close to 0. So,
I think
yes,
Pratik has a question.
Yeah.
Hello. Yeah.
Yes.
So before this, I mean, system fraction half, and after this, so is it? I mean, this is a relation. If you change v to v minus a, this should be the same thing, right?
For the pure state, yes. For the single pure excited state, yes, that should be true. That S of A is equal to S of A complet.
Yeah, but the previous in the previous slide, if you go to the previous slide.
Yes, that is yes.
This curve doesn't look in.
No. Yeah. So this was just we discussed. This is a plot against the energy density. Okay. So you fix
okay.
size. Yeah, and then you vary the energy density, and that is.
Oh, I see. Not the fraction. Okay.
Yeah. Yeah. If you plot it against the fraction, then yeah, again it.
Right. So another question I want to ask is that these mode occupation numbers, these this AIA dagger, this kind of things, they are also non-local things, right? But they are also incorporated into this generalized Gibbs ensemble. So does that mean this generalized Gibbs ensemble also incorporate this non-local conserved currents?
Yeah. Yeah, I don't know about this. I mean, at least. Yeah, sorry, I don't want to say something wrong. Yeah, I don't really know.
Okay.
But I think in some system, I forgot, probably it was the XXZ spin chain, which is integrable. And yeah, I think the history of that went like people included the local conserved charges. And then they saw that the system, it does not relax to that GE. But later on, they realized that there are these quasi-local charges. And then they said that, okay, if you include both the local charges as well as the quasi-local ones, and work with that GGE, then yeah, the final state description can be written in terms of that GGE. But I don't know this story very well, but I think it's for probably
so
the
statement is kind of that this non-local charges can be written in terms of local charge. Some about this local charges is a kind of thing. So the better. So if I phrase my question better, this generalized ETH, does this generalized ETH also include this non-local currents, some sort?
Yes, I think so. Yeah. I think probably for the XXZ, they had to include this non-local charge as well.
Okay.
Maybe we can stop recording now. Is it a good time?